As you mentioned on your introduction, I basically work always on the advancement of technology. So today I'm just actually focusing only just an idea what we have been doing in terms of advancement of laser technology for aerospace application. And obviously just have a look on how this basically affected the development of infrastructure and human capital, obviously here in South Africa. So I pick one of the technology that we have been working over the last few years, that is laser shock peening, as you mentioned. So I will give you just a brief background, have an idea what the initiative to develop the technology for South Africa was, and just an overview of some IP that we generated, some research and technology development project, and basically looking at the different collaboration that we created and obviously where we need to go. So just to give you an idea what laser shock peening is basically taking a very high energy laser, is a pulsed laser, and we target at the surface of a component, usually is a metal component. And as a result of that, we're creating basically a plasma on the surface that confined by usually water helps to create shock waves into the material. So we're basically improving the mechanical performance of the material through is peening with the laser, with a specific laser. So the technology has been developed in the past, but the majority of the work was coming from two commercial entities in the US, and they were obviously working on some military application or very thick component like turbine blades, and it was showing great performance. So if you're looking like in the graph, you can see that the moment that we're looking at the operative life of this component, we're actually expecting really fantastic improvement. So when I was still in Italy, we started to discuss with Airbus Germany at the time if we can actually use this technology, how we can develop that, and mostly apply basically to airframe structure. So actually really thin component that was a little bit different from what was done so far. So when I moved to South Africa, then I had this idea with me, and I was like, and then I discovered that we actually have the CSIR in Pretoria. At the time it was called the National Aerospace Centre. And we say, well, we can actually use laser, we can basically rent lasers, it's the rent-a-pool program that they have. And I try basically to starting to pitch the idea of creating a laser shock peening facility in South Africa. So there were being people obviously there that they listen. We organized the first European workshop. We obviously participated as well. And we tried to convince people that we can actually do this for South Africa. So basically in 2012, this is when the first moment when we started the activity. It was a strong collaboration in between us as Wits, the CSIR, but obviously we bring in the technical expertise and the industrial expertise was coming from Airbus. And obviously the financial support, because we need that from the Centre of Excellence in Material and the National Aerospace Centre at the time. So we created what we call it the South African Laser Shock Peening Initiative. Obviously, the target was to develop human capital, okay, but we really need also a lot of development in terms of infrastructure. We're basically just starting from zero. So we obviously dreaming of creating a South African, and obviously it's going a little bit different from the other one that were around the world, a laser shock peening facility. But the key was not to be a commercial entity at the very beginning, but actually give possibility to the South African and international research center in industry to develop first-hand knowledge of the technology, because up to that point it was basically just a black box that his industry will apply to component. That means that they will have a better understanding of the laser shock peening and how we can change it and adapt it to the specific type of application, especially in our case, as I say, was aeronautical airframe applications, so obviously thin component. So we started from scratch, and the nice thing is that we bring together a really big team of people. Obviously, we have people from the engineering school. We need to learn how to talk with the physicists, because obviously we knew what we wanted from the mechanical and aeronautical point of view, but we are not obviously physicists. And obviously we involved a lot of students. We started with master's students, and obviously we moved into PhD as well. So first thing first, so we basically need to figure out how it works, because we have seen a little bit of videos, but we really don't know anything about the technology. We need to learn a little bit about the laser, physics, and all of that. So we started with the basic research. We have what we call in the first proof of concept that was sitting at the CSIR. And this is exactly when we learn basically how to do things. Obviously, there is a lot of problems that you have to solve. So don't get scared, but this is basically what the process looks like and sound like. it's quite noisy. But if you see on the screen, this is basically what the surface looks like. So it's almost like the metal surface is looking a little bit of the shining because of that plasma that we basically generate on the surface, a small ablation that we have on the surface. But the result is obviously a component that we expecting to have better performance. So we move ahead, we invested, we obviously searching for more resources. And so now we basically have a very robust work cell for laser shock peening. We new positioning system, improved obviously power intensity and beam shaping capability, a water confinement system that we'll see later that was a big problem. And obviously we spend a lot of time in improving the monitoring and the diagnostic system that we have on this. So basically now what we have is what we call it a technology demonstrator, if you want. There's been some capital investment also from the CSIR. So at the moment, we actually acquire additional 2 Thales Saga lasers. So obviously, relatively big laser for targeting more industrial type of application. We try to implement this obviously with another KUKA robot. And basically here, we reached the point where we demonstrated that we can work for a lot of industrial processing as well. So basically working on real-world application, not just for pure research. Obviously, the activity is quite complex. As you see, you can imagine there are many, many parameters. There is a lot of different field of knowledge that we have to touch on. And in order to carry obviously the whole activity, understand really what the technology does for a specific type of material, there are different steps that you have to go through. Unfortunately, we are not in a situation where people come in and they say, this is my component, just pin it. It doesn't work like this. So obviously, we have to go through steps. I'm obviously not boring you with this, but I want just to talk a little bit more about the first steps that it was the fundamental investigation that obviously we found ourselves on because of some, interesting output. So as I mentioned, we had to go through, we had issues, it does happen. And one of the main issues that we have at the very beginning was the splashing and what we call in basically air and water breakdown, that it was causing a lot of problems. So while we try to understand what was happening, we had to obviously using more fancy toys, if you want to call it that way. And we started to investigate basically what was happening just through that thin layer of water that we are creating and how these basically interact with the laser pulse and all these, what we call cavitation events that happen. While we were doing that, and as I say, trying to fix all problems, we actually realized something interesting. We noticed that there was some regularity on how these different bubbles happen within the water layer, in between the first pulse from the laser and basically these cavitation events. So obviously here we were trying to fix a problem, but we discovered something interesting, and this is where we have our first ideas. Like we do have these basically timeline, and we call it the first bubble oscillation period. And it's always there, and obviously change depends on what is the energy that we deliver in other processing parameter. The idea was, can we actually use this idea as a diagnostic tool for laser shock peening? Because we look around all the international patents that are available, and we discovered that the majority of them are basically looking to the process from far. They are not really in situ, so they are really not looking at their direct interaction of the laser on the surface. So we follow the instruction of Wits Enterprise. We started to patent our idea, and now we landed up with basically a family of patents because the idea works. And now, obviously, we need to take this idea and make it into something functional, obviously for industrial application. So as per usual, we're obviously going out, we're starting to join people, we participate in events like the Innovation Bridge, and we actually secure funds to the Technology Innovation Agency in order to basically develop the IP. So we need a lot of, more complex toy, but in a nutshell, what we try to achieve is a configuration where we're using literally a pressure transducer, but you can imagine it's like a microphone, where we literally almost listening to the process while it is happening. So as a result of this, we basically obtained this. We obtained a system, and we call it the heartbeat of laser shock peening, because basically what happened is we can actually hear how the process works. A lot of technicians would tell you, I can hear if the process is going right or there is something wrong. This is basically what we're doing. We're listening to the process, and on the basis of that, we can guarantee to, obviously, the researcher of the customer that the process is done right, because obviously you want to make sure that you are delivering exactly what you are planning to deliver. So at this stage, we reach with this idea the technology readiness level 6. And obviously, we got some support from Wits Enterprise, some commercial partner as well. So we try to basically develop what we call a fully fledged diagnostic for that. So this was very interesting. So this is coming. At the same time, we obviously need to prove that this process works. And that means that we obviously starting a lot of projects with a number of my students to see how is the process actually really improving the performance of different components. So here I will just briefly go through the list of a lot of technology that we try to obviously integrate with laser shock peening to obviously maximize the benefit. So the first one we touched on it's laser beam welding. You see another laser technology that is one of the approved ones in the Aeronautical Centre to create what we call an integral structure. So instead of having different components that are joined or riveted together, we actually welded them directly with the laser. Unfortunately, this leaves behind some distortion, some residual stress is obviously something that is going to shorten the life of the component. And here the idea was, can we actually target the laser shock peening on the surface of these joints and see what is happening? So we have laser beam welding facility at the CSIR. We would obviously put on top of this some laser shock peening in the fashion similar to the process that I showed you before. And basically what we achieve is a complete reverse of the tensile residual stress, a relaxation obviously of all the distortion that we have here. So obviously here these are complex matter that going into X-ray diffraction and neutron diffraction, but basically the picture on your left is showing a lot of red. And, if you're working in what I'm working, red is a bad thing. It obviously means that you have some damaging stresses. And instead of applying laser shock peening, as you see on your right, we actually revert the situation to a full blue-green situation that is actually very good. So in terms of mechanical performance, what we saw is that if we integrating laser shock peening as a post-processing basically technology, we are not only drastically increasing the performance of the weld, but actually going beyond the performance of what the laser base material will do. So it basically means that we almost doubling the performance of the material itself, like the joint was actually not even there. So that means that obviously the process has big promise. Then obviously we need to try to understand how we apply to different components. So we started, you would see from here, a lot of different collaboration. In this case, for example, we collaborated with the US Air Force Research Laboratory and Coventry University. And what we did is that we tried to understand what is happening to components that obviously they don't have like a normal flat surface. And we discovered that also in this case, we're getting very nice result. Obviously, we need to, again, choosing in a proper way of parameters. And we also develop in parallel to that simulation tool. So in this case, we're talking finite element together, with colleagues through the African Laser Centre. That means we can use the data, the information that are coming from very simple sample that we can process and try to apply that to real component, obviously with much more complex geometry. And in this case, we can not only increase the life, but we can also do interesting things like correcting basically distortion that are coming from previous process, for example, machining or forming. So here we work, for example, in a real application with the National Aerostructures as an African company on a component that was machined, but obviously it's one of the very expensive one, but unfortunately it comes out of machining with some distortion. And here then we came in and with a targeted, obviously, application in different area of laser shock peening, we managed to bring back basically the component completely to spec. So this is also very interesting because that means obviously we can restore, if you want, component that otherwise will have to be thrown away. And we carry on with this activity now with colleagues from Airbus and from Italy to try to see if we can actually correct this, even during the assembly phase. You maybe have panels that are coming during the assembly phase of an aircraft and they are out of spec. Again, instead of throwing away everything, the idea you will be have inside there's a Shock Peening station that can targeting a certain point on the surface and basically bringing back the component to the desired shape. Same thing obviously was applied to other type of joints. For example, friction welding is what we call in a solid state process. This was actually the technology that I used for my PhD, so I can bore you to death on this. And it's a fantastic process because it really has minimum defect. There is always the possibility that you have a small imperfection at the back of the weld. So even here with one of another colleagues from Germany, we try to target just the back of the component to see even if there are small cracks or imperfection, equally lack of penetration, we can actually reverse the process. And we got a very, very, very nice result as well. Unfortunately, in aircraft, it's very common that you have a lot of small cracks. That is obviously people don't like to hear that when they fly, but unfortunately, it does happen. But the important thing is that it's not a crack out of control. With obviously a lot of friction mechanics work that we're doing is actually making sure that we're assuming that a crack is there, but just making sure that it is not propagating too fast. So that means it's still safe to fly, and you use obviously that specific airframe component within different obviously interval for maintenance. So here is one of the first work that we did, is trying to use laser Shock Peening, introducing some basically almost patches of stripes, if you want, of laser Shock Peening in critical area. And we basically increase what we call the fatigue life of six times. So a really, really good result. So then we obviously talking and pitching the idea to other colleagues in the UK here. We spoke with the guys in Cranfield, and together with the colleagues from Airbus, we moved this idea to real fuselage joint, so that traditional lap joint that you have it. That obviously is the point where the majority of the cracks are starting. So applying the South African laser Shock Peening in different configuration. Also in this specific case, we actually saw improvement on performance of basically 2 times. That means, again, if a crack is there and you start, it will still take basically double the time. So there is much more, let's say, possibility also for the technical team to identify and correct the issues there. A big drive in the country has been, and in other, for example, here again in the UK, has been machining of titanium. So I have a full other team of colleagues also from the School of Chemical and Metallurgical Engineering that are working into the development of new cutting tools so basically cutting titanium in a more efficient way. And obviously we have a lot of activity that are going on, try to make obviously technology more green. But the idea that we have, it was like, okay, now we're working on the chemistry of this cutting tool, but we can also use laser Shock Peening there, because up to now we always use it on metal material. Now here on cemented carbides, we honestly are not 100% sure how it actually works, but it works. So we actually saw that these cemented carbide that we are busy developing for another process are actually drastically improving the fracture toughness after we apply the laser Shock Peening on the surface. And also the wear, so obviously the cutting insert while it's cutting is actually lasting much longer. So again, here we have the idea, we're protecting with the patent. Now we have a couple of patents here, and we're looking for industrial partner on this. But that means actually laser peening can actually have a right big type of application also in this environment as well. When we're talking laser technology, additive manufacturing, so metal additive manufacturing, it's a massive drive in South Africa. So again, here the idea was to come with laser Shock Peening and to see how we can potentially fix problems that are inherently part of the metal additive manufacturing process. So usually a quite rough surface, adverse residual stresses, possibility of porosity. So we tried laser Shock Peening in collaboration with the colleagues from Central University of Technology on titanium additive manufacturing. And we use it for both, let's say, aeronautical application, but also on biomedical, because obviously there is a lot of work that is going on there. And what we saw is that laser shock peening, even without any protective layer, is actually capable of removing some of the features that are coming from the laser additive manufacturing. It also created some interesting surfaces that are actually very beneficial from the biomedical point of view. So again, we have a technology that post-processing technology that combined with another advanced field is actually showing very promising result. We're also developing new alloys, because now why we want to stop? Obviously, we want to do additive manufacturing, but we also try to develop new alloys for additive manufacturing, and then potentially post-processing also with laser shock peening. So we're starting to be creative in that direction. Colleagues from aerospace were very interested on this. So currently we're working again on titanium. We actually just acquired a new additive manufacturing machine, so it's coming to the lab very soon. And we saw that applying laser shock peening, we obviously have, again, very, very good result with their security, the porosity. So this is obviously a big achievement, especially for aeronautical application. But we also try to see how we can develop technology. So, for example, new inspection method, a new testing method that can simplify the adoption and the uptake of additive manufacturing laser shock peening within the aeronautical industry. I just finished, very recently, with one of the colleagues from CUT. He's finished his PhD, and we're working now on real components. So not just sample, but here we're talking at, for example, landing gear that are being manufactured by additive manufacturing, and obviously so 3D printing on titanium alloy. And the plan is to moving forward and try to apply now also laser shock peening to this, so to see what kind of real improvement we have for proper aeronautical components. And then at the same time, obviously, we don't do only research. We try to reach out to industry, but not just international industry, but also South African partner. So, for example, in the space of what we call maintenance, repair, and operation, we obviously talking with colleagues at the time of the South African Airways to try to use it not just the conventional shock peening that is already in use and is already certified. It's like a standard conventional process. But we show that obviously with laser shock peening, we're obtaining massive results. So one of the potential applications would be, for example, to have an LSP station at, the Johannesburg or Tambo airport, and obviously try to process the critical component on site, especially if you have some defects that are starting to appear. Obviously, I don't need to tell you that we have a lot of issues also in the power generation sector. So one of the big projects that we currently have that is based at the CSIR is working with ESCOM to try to see how we can optimize the laser shock peening process for turbine blades. That means that we're going to target this critical area at the root of turbine blades, because again, here we're talking of components that are extremely expensive. So obviously the cost of, if a damage of a broken blade, they are really massive. So anything that can improve the performance and can obviously extend the life of an aging fleet, basically, of blades is going to be extremely helpful. We touch base also on mining. Again, laser shock peening can actually use, as we show, for the cutting insert on very hard material, where other technology are failing, because obviously they don't work on hard material. And we saw very good result also on site. We actually find a portable LSP unit. So obviously moving mining component to a lab is going to be difficult. So we actually try to create a situation where we have a portable laser unit that we can take on site on the mining space. So what we did is, over these few years, just using laser shock peening and obviously the correlated technology, is to create a very large network of people. As I say, a lot of different university, research center, institution, funding institution, but we try to target also a lot of the industry, because what we want is actually practical research, applicable research into the environment. And then, as I said, this is critical not just for us, but for all the students that are involved into the process, because this is obviously creating skill and expertise and knowledge base capability, they can go out and apply, obviously, on industry, local industry, obviously, or international industry. In order to do that, we are obviously trying to partner with people. And in the past, obviously, we went through Horizon, European big project on development of the technology. Currently, we are busy with an Erasmus Plus project where we join together colleagues from different institutions in South Africa, Kenya, Botswana, Namibia, Germany, and Italy. And we actually created a consortium that is targeting the development of his knowledge within academia. So that means we're training, obviously, the new colleagues, like younger colleagues, on laser-based technology, but we're also developing postgraduate courses, okay, that obviously we can offer to students, but also in theory as short courses to the general public in order to increase the knowledge of everything that can be done with laser. Not just obviously laser shock peening, but a lot of other technologies you've seen that can deliver and can be integrated into the manufacturing plants and obviously improving their performance. So here's the website. You can start to have a look. Obviously, something that we just started, but we are expecting big things from this activity. So we show that basically we have strength. We can optimize parameter and create solutions for a specific type of application. But this obviously is just a start. In order to successfully and fully transition the technology from the lab to the production floor, I think there is still work that needs to be done. As I say, obviously making more aware the industry of what can be done. Sorry. And then we can basically the goal is try to deliver a manufacturing solution that is an advanced one to the South African obviously industry. Again, here is there are different ways to do that. We can integrate obviously the development together with the industry, but we're also looking at solutions like, for example, like a spin-off, a dedicated facility, somewhere, for example, in Centurion. There can be a central point where people that they struggle with any type of failure, mechanical failure for metal component, come in and look to us for solution. So obviously it's a big thing. You just put in a picture here, but there are many, many more people that have been involved into the process. And I do thank you. I think I try to stick to time, but I'm almost there.
I think it is just a fantastic amount of work that you are doing at your center. And I hope that people have noticed that that this is really cutting edge work and innovation. I mean, you're innovating as you go along, isn't it? You're solving problems all the time.
No, yes, this is, unfortunately, sometimes we have this situation where people just pitch and they say, this is broken, can you fix it? Okay, so obviously we are not, and I'll try to explain it's a little bit more complex than that, but it is obviously like all the advanced technology, we will need to obviously to learn how to tailor, but that's why we're developing a lot of other tools, like, for example, simulation, that help us to accelerate the uptake of the technology to specific material, to specific component, to specific geometry as well. But there is obviously a substantial amount of work that can go there. I would say that maybe you can't target exactly like a super cheap solution, but what we try to obviously to achieve is something that works on more, let's say, costly component, where obviously the repair, or let's say the fatigue life extension solution that we're proposing is much more economical viable than obviously throwing away and recreating, remachining the entire component from scratch. So I would obviously technology, the cost of the technology itself is obviously coming down because the laser cost is also coming down. So even one of the core point of the South African approach, if you want, to laser shock peening, is actually using what we're calling off-the-shelf laser. So that is drastically cutting the cost, because if otherwise other solution, say another research center, they actually creating their own laser or is a custom made. So that is obviously drastic increase in the cost. Here, what we're looking is to integrate a quick solution into the production process. It can be during production or, as I say, during maintenance. So we look at portable solution, and it's something that in theory we can apply on site at the airport or wherever the problem happens, and just laser pinning the surface, and we are ready to go, or integrating directly with the production line in a very efficient way. So we're talking here Fourth Industrial Revolution. One of the plan that we have, and I have a number of students that are working on this, is to have a station during assembly that can scan the surface, check if the geometry is in spec. If the geometry is not spec, then the laser comes out and basically just targeting the surface and bring everything back into obviously the desired geometry on site. So this is why laser technology actually have a big potential to be integrated in what we imagine to be the industry of the future, because they are highly reliable, robust, controllable. So you know exactly basically what is happening. We kind of removing that randomness that might be connected to other, with other more, let's say, mechanical processes.
Right. I think this is a totally different take on the automation in manufacturing. When we think of advanced manufacturing, we often think of everything being automated and people being taken out of the equation. But here you have specialists who know what they're doing, and it's very focused. So they go to a particular place on the assembly of an airplane, for example, and they have to set the laser in such a way that it will do what you want it to do. Is that right?
Yeah. No, that's basically it. Obviously, we try to reduce the chance of error. Obviously, try to standardize, if you want, the application process. But there is obviously an element where you will still need at this stage, obviously very specialized technician to be on site. At the same time, going back to that first patent that I mentioned, things like that in situ monitoring system is actually helping also people that don't have maybe that 100% experience, because it's literally helping you to understand if the process is correctly applied. So that, if you want, is one of the first steps in the direction to have a fully automated application, where the technician might be able, obviously, to guide the process, but doesn't have to be on site, can maybe remotely control what is happening there. Also because we're talking very high energy lasers, so there is all the health and safety that goes with that. So you don't want maybe to be too close as well. So yeah, if you don't want to get like extra 10, but we obviously need to be very conscious of health and safety, integration of the system with the production line, and try to make it as easy as possible for industry to actually uptake the technology. Because if it's too complicated, then people will, I don't know, I'm just going back to the normal mechanical one. We actually want to make people train them, obviously increase the base knowledge, but we, try to make it easy for people to use it.
Right. Fantastic. Oh, I am in awe once again. Is a question, I think. Let me just see. From Busisiwe Aland. Prof Polese, your work on LSP diagnostics beautifully bridges physics, robotics, material science, and aerospace. Well put. And we're thinking about growing this field in South Africa. What kind of infrastructure would be needed at the school level to spark interest and build foundational skills? And how can universities in South Africa play a catalytic role in building a pipeline from classroom curiosity to advanced research and industry innovation?
I think what we can do is that there are different, obviously, initiatives. I can't remember if it was last year, there was the photonic year. So there have been obviously a lot of what they call in photonic initiative across the country. But I think one that works very well is what we call in the African Laser Centre. And we're usually running workshop also for students, postgraduate students. There is obviously a group of people that are working within that space, a lot of postgraduate students. They're doing a lot of very nice outreach program And they try to explain, if you want, is laser for dummies, okay? And even for myself, when obviously we started, I'm an engineer, I never worked with laser, I knew nothing about, the physics of the laser. So I think that is great because they're showing you what you can do with laser, and it sparks interest. It's actually a very nice workshop that the guys are running. So I think they call in the student chapter of the African Laser Centre. And that I think is a great starting point. You can even pitch it obviously at different level, from school, but also through university if you want. And that's where people starting to understand how the physics works. Okay. And then, exactly like we did, the moment that you have an interest, you would see that even on school or other school, for example, electrical information engineering, there is actually a lot of people that they're using laser for different technologies. So obviously we breach into the physics department, and we try to put together our strength. So we know what we want, maybe from the engineering point of view, and we need someone patient enough from from physics to explain us how this works. But I mean, just reach out and I can give you all the detail. I think there is actually possibility, to do that. And then it's almost like a road show. The cost of let's say introducing laser, it's a little bit more complicated because, as I say, unfortunately, there are also a lot of health and safety issues that you need to tailor. So procurement within university can be quite challenging. However, the rental pool program that I was referring to, that is what we're starting with, and is the program we still are here. So we are forever grateful to the SDI and the CSIR to let us use it. It's literally this. They're renting laser. So you can either rent laser at the CSIR in Pretoria, so you have basically laser time. So you have an idea, you go in there, and there are obviously the physicists from the CSIR that help you to create what you want. Or if you have the capability, you can actually rent the laser and take into your institution, obviously, with creating the condition there to operate the laser on site. And there is a number of colleagues across the different universities that actually operate into that drastically cut the cost, because the cost, obviously, the laser, there is a big range. It's like a car. There's a cheap car and an expensive car, but it's not cheap. But that drastically cut you the cost, and they really help you. And as I say, for us, it's been fundamental because we start with them and we stay with them. All laser are actually still at the CSIR through the rental pool program. So I think that is a brilliant initiative. And, at least for us, it works fantastically well.
Oh, no, that's good to hear. That's very good to hear, because the equipment and infrastructure are so important, and it is the expensive part. Well, it's the capital part of the whole endeavor. Prof Claudia Polese, thank you very, very much for your presentation, for taking the time today, and for just sharing the phenomenal work that you are doing. I'm also just so proud of you as a woman in Women's Month, for the kind of work that you are doing, which is normally regarded as a man's preserve. But you are just such a stunning role model to us all. Thank you very much indeed.
Thank you. And as I say, it's great that even in engineering, we're struggling obviously to retain female students, especially for postgraduate studies. And this initiative actually created very nice engineer. We have a nice female engineer. They came through the program and they managed to grow through that. Obviously, the number are not
big.
Not big, but it's coming. It's coming. It's the
yes,
wave
yes.
coming.
Yes.
There has definitely been an improvement compared to a few years ago. So we're coming.
You're fantastic. Thank you very much. Okay.